Hey, welcome back to Math with Patrick. Today is August 30th, and we're solving problem number 242 from the Daily Epsilon calendar. And as today is the 30th, the answer should be 30. That's why there's a 30 right up here in the corner. And with these instruction list problems, the assumption is that we're solving for x. So x should be 30 today, and I don't want to use that information to learn more about the problem. I want this to be enough to know that x is 30 for today. So I'm seeing that x is some number, and it's the same thing as 2 to the power of r, and 3 to the power of s, and 5 to the power of t. Now, I'm already thinking that I'm running into some kind of trouble here, as in there won't be a good whole number solution. Because, for example, if we try checking out some powers of 2 real quick, here are the first few powers of 2. We can check out some powers of 3, so here are the first few powers of 3. And we can check out some powers of 5, so we got 5, 25, 125. We're never going to get a whole number that lines up for all three of these. The prime factors of 32 are all just 2's, just as the prime factors of 81 or anything in this list are just going to be a bunch of 3's. So we're never going to get the same number in kind of for x, I guess, or in any equation here, unless we try using powers that aren't guessable numbers. They're not going to be easy whole numbers that are going to line up these numbers. So it'll be a little bit of work is what I'm seeing already. And then we have some kind of condition that relate r, s, and t together, where the reciprocal of r, s, and t, or the sum of the reciprocals of r, s, and t are all going to be, or is going to be 1. So the sum is 1. And I'm seeing let's say r is, let's just pick a number 3 real quick. So that would make x 8. Then we would need to put that 3 down here. And then this 8 would then suggest something about the number s. Again, if I pick a whole number here, I'm not going to get a whole number here. So s, I'm thinking would be about the number 2, right? 3 squared is kind of near 8. Of course, it's not actually the number 2, but then we would put that number 2 here. And then 5 to the power of 1 is kind of closer to 8 than 5 to the power of 2 is. So in this case, t would be around the number 1. But then this is a little bit of an issue where I'm already adding the number 1, and then I have a half and then a third. So clearly this side is bigger than 1. So I guess to me that this suggests that my denominators down here need to be bigger. So these exponents need to be bigger. And so at least right now I know the answer is bigger than 8. Just kind of plugging in a number, trying out the logic. What do these equations even tell me? Well, now I know x is bigger than 8, so that bodes well. But I don't think guess and check is really going to push me anywhere further closer to a right answer. I think I need to try something else. I don't like how we have so many variables here. And I think it would be nice to be able to just remove all notices of s and t and hopefully have some kind of expression with r in it instead. And I think I'm able to do that by grabbing this equation right here. And I think I'll get something out of this where I'll be able to replace all of my s's with something with r. I'm just trying to reduce the amount of variables I have. So 2 to the r is equal to 3 to the s. I know that anytime I have a variable in the exponent, I can knock it down by taking a log of both sides. And I'm just using the natural log because that's just kind of what I'm most used to. There is a log rule that lets you essentially take an exponent on the inside of the argument and take it out front as a coefficient instead. So now I have both of those variables a little bit more accessible, I suppose. And then in the end, I want to replace s. That's my goal, at least right now. And so I should isolate s. And I'll do that by dividing both sides by the natural log of 3. So now I have some kind of expression for just s, and it's going to be this. And I think I'll do the same thing with t. where I'll just, instead of doing 3 to the s, I'll just put 5 to the power of t right here. So that means 5 to the power of t would go right here, and that means t would be the thing that is now there instead of the s. And then instead of a natural log of 3 in the denominator, I would get a natural log of 5. So let me not mess up my previous work. This still mattered. But now I get, I think, r times natural log of 2 over natural log of 5. And this is my expression for t. So let's maybe just rewrite everything, replacing any s or t I see. So x is going to be 2 to the power of r, which should be the same thing as 3 to the power of, and then s right here is r times natural log 2 over natural log 3. And then t is going to be r times ln 2 over ln 3. I really don't see anything out of this first equation, so hopefully the second one is going to give me something. We have 1 equals 1 over r plus 1 over, and then s is, okay, r times ln 2 over ln 3. And then t is r times ln 2 over ln 5. I know that anytime you do 1 divided by a fraction, it's essentially just taking the reciprocal. So I could simplify the second and third addends right there by just flipping them. We'll have ln 3 over r times ln 2, and then ln 5 over r times ln 2. We still have everything else as is. Now I'm noticing we almost have a common denominator, right? These are identical. And so the only thing that I need to do to the first fraction is multiply on a ln2 to get a common denominator. And so I'll multiply the same value to my numerator to get an equivalent fraction. And then the 1 times, that doesn't really do much. So I'll have this. Let's get the common denominator all together. So r times ln2 on the bottom. And then we could put all of our addends in the numerator. And then, there's another log rule that we can use. The sum of logs is the same as the log of the product. So in other words, we could take natural log of 2 plus natural log of 3 and call that the natural log of 2 times 3. Anytime we come across log rules, I always double check if this is actually the case. So, I know this one by heart, so I wouldn't do this one. But just to confirm, if you're not quite sure that this rule even works, I'd recommend try it out on a calculator and you're gonna get the same number. So we could even do that all at once. I think I could do natural log of 2 times 3 times 5 is the same thing as that numerator that I have right there. And I guess what's best is to isolate r, right? Because, that's one of my variables. Might as well. I'm one step away from isolating r. Let's make this 2 times 3 times 5, 30, because that's 6 times 5. And then I'll multiply both sides of my equation by r just to kind of cancel the variable and stick it over on the left side. And 1 times r is just r. So now I get a nice expression for what r is. It's the natural log of 30 divided by the natural log of 2. And we could even go one step further with this one. I'm going to use the change of base formula, but kind of backwards, actually. Normally the way that I use the change of base formula, let's take a look at maybe log base 2 of 10. Normally when I use this change of base formula, I know that I'm allowed to rewrite any logarithm as log base whatever I want of the argument divided by log base the same thing as the original base. So these two expressions here and here are equal to each other by the change of base formula. And what's cool is I can choose any base I want, hence the name that I'm changing the base. So this could be the number, say 10, if I really wanted it to. And then that lets me maybe simplify the numerator to get a 1, because log base 10 of 10 is 1. And essentially, this just lets me be a bit more creative with what I'm doing with my logarithms. And so I'm able to say something like log base 2 of 10 is the same thing as 1 over log base 10 of 2. And that's a cool relationship. So anyways, I'm using that change of base formula backwards though. I notice that my natural log, which has a base of e, is the same right now. And so I could actually rewrite this as log base 2 of 30, right? Because if we did it backwards again, I know that I could do log base whatever of the argument over log base whatever of the original base. And then it just so happened that my base here for these natural logarithms was e. So I'm confident that r is equal to log base 2 of 30. The way that I read logarithms is that this is almost like an instruction. It's asking you, how many 2's do I need to multiply up to get to 30? Like log base 2 of 8 asks, like, how many 2's do I need to multiply to 8? Since I need 3 2's, the result of this logarithm is 3. And so this one is a little bit harder because like the nearest power of 2 is like 32. 16 would be the one prior. And so I know that log base 2 of 30 is going to be like just shy of the number 5, right? Because 2 times 2 is 4, 8, 16, and then 32 is the fifth 2. And so 5 2's overshoots the number 30. So log base 2 of 30 should be like 4.8, 4.9 maybe. Essentially kind of close to 5. But I don't think the approximate value really matters for this problem. R is the precise value that when I raise 2 to the power of r, I get 30. That's kind of the meaning of this equation. We can rewrite it as an exponential equation where 2 is our base, r is our exponent, and 30 is our result. So 2 to the power of r has to be 30. So 2 to the power of r has to be 30. So x is 30 for today. So there is our solution. I guess it kind of boiled down to, or it came down to going down to one variable instead of 3, and then using a lot of different log rules to then figure out what that variable is supposed to be. And then rewriting our logarithmic equation as an exponential equation really clears it up for me that yes, all of these numbers are indeed just 30. So something that I don't really know yet for certain is like what actually happens when we plug in like log base 2 of 30 right here. And I'm assuming this number right here would then be like log base 3 of 30. And this one would be log base 5 of 30. And just looking at it like this, I don't yet see why this is equal to the number 1. But I'm pretty sure the algebra steps involved in verifying the secondary equation are essentially somewhere hiding in the algebra that I already did. So I trust that x is 30 for today, and I think we can be all done. So thanks for coming along as always, and I'll see you tomorrow. Bye.